Forming this is lab 4 oscillations. The purpose of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring using the fundamental physics principles and the techniques found when analyzing a vertically oscillating mass spring system. I aim to predict and understand this motion. And so the fundamental physics principles were the energy principle, where delta E is equal to W, which is equal to 0, and so the work is equal to the kinetic energy, the gravitational potential energy, and the spring potential energy, and so the summation of all of that is equal to 0. And then the gravity force, the gravitational potential energy, the spring force, and the spring potential energy and kinetic energy formulas all through here. And then Newton's second law with the derivatives of like the position update formula and the velocity update formula. And so the physics models, so here is the experimental model found using Tracker. And so I set the origin as the attachment point at 0, 0, 0 meters. And then the axes, we had the right being positive x and the up being positive y. I started at frame 6 and I ended at frame 105. Then here's the computer model using the data that we extracted from the Tracker model. So the blue ball is the predicted motion, the red ball is the experimental motion. And so it shows the change in energy in the two positions between the two models. And so the initial conditions, the system is the ball, the spring, and the earth and the surroundings, there are none. The initial position is the vector point negative 0.09881, negative 0.637, 0 meters, and then the initial velocity is 0, 0, 0 meters per second. The mass is 0.402 kilograms. And so I solve for T, S, and K, really like L naught, because it's to find S, but finding T, I use the oscillation in the Y, and so I use these 5 peaks, and I found 4 different oscillations, and then, or 5, and then 5 different oscillations, and averaged them, and I got 1.5 seconds. Then I plugged that into the formula for spring stiffness, and I got 7.053 newtons per meter. Then I used that, and I plugged that in to having the gravity force equal to the spring force because it's at rest, so it's in static equilibrium, and then I got 0.141 meters. And so here's the code. I have the same initial conditions here, and the time delta T is due to the difference between frames. And then here we have gravity, another constant. We have the spring constant we found. We have L naught, and then we have L equaling the ball position minus spring position, L hat equaling L over the magnitude of L, and S equaling the magnitude of L minus L naught. And so here we're using the kinetic energy formula to do that, the gravitational potential energy formula to do here, the spring potential energy formula here, and then delta E equaling the summation of all of these. And so that is shown here. And then we have delta kinetic energy equaling kinetic energy final minus kinetic energy initial, delta potential energy equaling potential energy gravitational final minus initial, the potential spring energy final minus initial, and then E equaling 0 and delta E equaling 0 because they all will cancel out. And so here we have the gravitational force, negative ball's mass times gravity, the spring force is shown 4, and then F net equaling the spring force plus the gravity force. And then using Newton's second law, I updated this ball velocity update formula and then the ball position formula. And then here is the model versus the experiment and my explanations for error. And so as you can see that in the X position, the model becomes less and less accurate to the experiment. This gap is growing between here. And so this is likely due to a force that was not accounted for in the model, which I think is air resistance. And so it's causing the F net that caused it to move initially to slowly slow down. And so it reaches these peaks sooner because it's not traveling the same way, and so it's causing it to be greater and less accurate. And then for the Y position, it's very, very similar, the experiment and the model, but you can see the experimental does not hit the same peaks, not as high, and so this is also likely due to air resistance, causing it to go up and down a shorter distance. And so is the energy principle satisfied? I say it is, because you can see here that the spring force and the gravity force and the kinetic energy are all canceling out. They're in opposite directions, and it's leaving delta, the change in energy equal to 0. And so the period of oscillation in the x-axis and the y-axis, so you can see that the T here is for the x is greater than the period of oscillation for the y. And so I believe that this is simply because it's reaching these peaks at a greater amount of time. And this is likely due that it's traveling a greater distance. You can see that these peaks are farther apart. From 0.1 to negative 0.1, that's a 0.2 difference. But from negative 0.65 to negative 0.75, that's only a 0.1 distance. So this time is going to be shorter. But this time is going to be longer because it's traveling a greater distance. And this is also just because of the different forces that are acting upon it. And that's all.